Look up at the night sky, and it appears full. Stars scattered across darkness, faint clouds of light, distant points that suggest a crowded universe. But this impression is deeply misleading. In reality, almost everything you see is separated by enormous distances of near-perfect emptiness. The most surprising fact is not that the universe contains matter, but that it contains so little of it. Today, we will examine why the universe is almost entirely empty, how this emptiness behaves, and why everything we observe depends on it. If you enjoy calm, precise explanations of overlooked scientific facts, consider subscribing and liking the video before we continue. When scientists say the universe is mostly empty, they mean this quite literally. If you remove stars, planets, dust, gas, and all visible structures, what remains is an immense volume where particle density approaches zero. Even inside galaxies, where matter is considered concentrated, the average distance between stars is measured in light years. Within atoms themselves, the nucleus occupies a region so small that if an atom were the size of a cathedral, its nucleus would be a grain of sand at the center, with electrons existing as probability distributions rather than solid objects. Most of what we experience as solid matter is structured emptiness governed by electromagnetic forces. This conclusion is not theoretical speculation. It comes from direct measurements. Astronomers calculate stellar density by counting stars in defined regions of space and measuring their separation. Particle physicists determine atomic structure through scattering experiments, such as the famous gold foil experiment conducted by Ernest Rutherford in 1909, which demonstrated that atoms are mostly empty space. Modern experiments using particle accelerators continue to confirm this structure with extraordinary precision. The emptiness of space is not uniform, but it is consistent in one critical way: matter is rare. Even interstellar space, which contains gas and dust, typically has only a few atoms per cubic centimeter. By comparison, the air you are breathing contains roughly 10 billion molecules in the same volume. Intergalactic space is even emptier, with densities that can drop to 1 atom per cubic meter or less. These values are measured through absorption spectra, where distant light passes through space and reveals the presence of atoms by the specific wavelengths they absorb. Despite this scarcity, emptiness is not equivalent to nothing. What we call vacuum still exhibits measurable physical properties. Quantum field experiments show that even in regions devoid of particles, fields still exist. These fields produce observable effects such as the Casimir effect, where two uncharged metal plates placed extremely close together experience a tiny but measurable force due to changes in vacuum energy. This phenomenon has been repeatedly observed under laboratory conditions and precisely matches predictions derived from quantum electrodynamics. On larger scales, emptiness plays a stabilizing role. If matter were significantly more concentrated, gravitational interactions would dominate too strongly. Stars would collide more often, planetary systems would be unstable, and galaxies would rapidly collapse into dense clusters. Observations of galaxy motion and structure show that their long-term stability depends on the vast distances between objects. These distances are not accidental. They are a direct consequence of how matter distributed itself during the early stages of cosmic expansion, a process inferred from background radiation measurements and large-scale structure surveys. Even within stars, emptiness is essential. Nuclear fusion occurs in the core of stars not because particles are crowded together, but because extreme temperature and pressure allow rare collisions to overcome electromagnetic repulsion. Most particles in a stellar core pass each other without interaction. Fusion happens precisely because space exists between particles, allowing energy to be transferred gradually rather than catastrophically. This balance is confirmed by neutrino detectors on Earth, which measure particles produced directly in fusion reactions inside the Sun, matching theoretical predictions with remarkable accuracy. On human scales, emptiness is hidden by forces. When you touch a solid surface, your hand never actually contacts the atoms of that object. Instead, electromagnetic repulsion between electron clouds prevents overlap. The sensation of solidity arises from force interactions across empty space. This has been demonstrated through atomic force microscopy, which measures repulsive and attractive forces between individual atoms without direct contact. The emptiness of space also allows light to travel. Photons move through vacuum without resistance, preserving information across billions of years. When astronomers observe distant objects, they are detecting light that has traveled through nearly empty space with minimal interference. The clarity of astronomical images is direct evidence of how little material exists between galaxies. If space were dense, light would scatter and blur, and long-distance observation would be impossible. Another overlooked aspect of cosmic emptiness is temperature. In near-perfect vacuum, temperature approaches absolute zero because there are almost no particles to carry thermal energy. Measurements of background radiation show that empty space maintains a temperature just a few degrees above absolute zero. This value has been confirmed by satellite missions such as COBE, WMAP, and Planck, all of which independently measured the same result using different instruments and methods. Emptiness also governs time scales. Because matter is sparse, physical processes unfold slowly on cosmic scales. Galaxies take hundreds of millions of years to rotate. Stars burn for billions of years. These long durations are possible because interactions are infrequent. In denser systems, energy would be exchanged more rapidly, leading to shorter lifetimes and violent instability. Observations of stellar evolution across different regions consistently support this relationship between density and longevity. Even cosmic radiation reflects emptiness. High-energy particles travel vast distances before encountering matter. Detectors on Earth observe cosmic rays that originated far beyond our galaxy, indicating uninterrupted travel through near vacuum for millions or even billions of years. Their trajectories and energy levels align precisely with models based on sparse matter distribution. What is perhaps most counterintuitive is that emptiness is measurable. Scientists do not infer it philosophically. They quantify it. Density, pressure, particle flux, radiation intensity, and gravitational influence all provide converging evidence. Independent measurement techniques, from spectroscopy to particle detection to gravitational modeling, all arrive at the same conclusion. The universe functions the way it does because matter is rare and space is dominant. Every structure we observe exists not in spite of emptiness, but because of it. Distance prevents collapse. Separation allows stability. Vacuum enables motion, light, and time to unfold without constant interference. The universe appears dramatic and full when we look at it, yet its underlying nature is defined by absence rather than presence. And the most precise measurements we have continue to confirm this simple, unsettling fact. Existence operates within vast regions where almost nothing is there at all. The same pattern appears even when we examine motion at the smallest measurable scales. In particle detectors, vast volumes of space are monitored continuously, yet interactions occur as rare, isolated events. Most particles pass through these detectors without ever colliding with anything. Neutrinos, for example, travel through entire planets as if nothing were there. This behavior is not theoretical. It is confirmed daily by underground observatories that register only a handful of interactions despite trillions of particles passing through every second. These measurements reinforce the same conclusion: emptiness is the default state, and interaction is the exception. This scarcity also explains why structure is fragile. A galaxy is not a solid object but a delicate arrangement of motion. Stars orbit a common center, rarely approaching one another closely. Computer simulations based on observed mass distributions show that even small increases in density would disrupt these orbits over time. The persistence of galactic shapes over billions of years is direct evidence that space between stars must remain vast. Otherwise, gravitational encounters would accumulate and erase these structures. Even clouds of gas, which appear dense in astronomical images, are remarkably thin. When astronomers describe a molecular cloud as dense, they often mean a few thousand particles per cubic centimeter. These clouds can span many light years, yet a spacecraft passing through one would encounter conditions far emptier than the best vacuum chambers on Earth. This is confirmed through radio observations of molecular emissions, which reveal how rarely particles collide even in these so-called dense regions. The concept of emptiness also shapes how energy moves. In sparse environments, energy spreads slowly and predictably. Shock waves, radiation fronts, and particle streams propagate without constant interruption. This is why supernova remnants expand in smooth, spherical patterns for tens of thousands of years. Their shapes match models that assume extremely low surrounding densities, a fact verified by X-ray and radio telescopes observing these expanding shells. On the scale of atoms, the same principle governs chemistry. Chemical bonds do not involve particles touching in the everyday sense. They arise from shared electromagnetic fields extending across empty space. Spectroscopic experiments confirm that bond lengths are orders of magnitude larger than the particles involved. What we interpret as material connection is actually a stable arrangement of forces acting across absence. Even pressure, a concept associated with crowding, behaves differently in near vacuum. In space, pressure is not generated by confinement but by rare impacts. Instruments on spacecraft directly measure this by counting particle collisions over time. These measurements consistently show that pressure drops dramatically once a spacecraft leaves a planetary atmosphere, approaching values so low that mechanical resistance becomes negligible. As measurement techniques improve, the picture remains unchanged. Whether using gravitational lensing, particle scattering, radiation detection, or direct sampling by probes, the data converge. Space is not subtly empty or partially empty. It is overwhelmingly empty, with matter existing as isolated islands separated by distances that define how everything behaves. What makes this difficult to intuit is scale. Human experience evolved in an environment where distances are small and interactions constant. On larger scales, those assumptions fail. The laws remain the same, but the spacing between participants changes everything. When spacing increases, interaction becomes rare, stability increases, and time stretches. This is why emptiness is not a background detail but a controlling factor. It determines how long systems last, how energy flows, how structures remain intact, and how information travels. Remove that emptiness, and the behavior of matter changes fundamentally. Every observation, from the motion of galaxies to the structure of atoms, continues to point in the same direction. The universe we observe operates in a state where almost all volume contains almost nothing, and where that absence is not a flaw or anomaly, but the condition that allows order, motion, and persistence to exist at all. This understanding also reshapes how scientists interpret collisions. Because space is so empty, most encounters between objects are governed not by direct impact, but by long-range forces acting across distance. Gravitational interactions begin far before objects approach each other closely. Electromagnetic forces influence charged particles without contact. Measurements of orbital decay, particle deflection, and energy transfer all confirm that interaction usually occurs without anything ever touching in a classical sense. The rarity of collisions explains why extreme events are noticeable at all. When two stars do collide, or when a dense object passes through a sparse region, the event stands out precisely because it is so unusual. Astronomers can identify these occurrences clearly against a background where nothing typically happens. This contrast allows precise study, turning emptiness into a kind of experimental control condition on a cosmic scale. Emptiness also limits how information spreads. Signals weaken with distance not because space absorbs them, but because they disperse across expanding volume. Radio transmissions, light pulses, and particle beams all obey this principle. Engineers test this regularly by sending signals to distant spacecraft and measuring signal loss exactly as predicted by inverse square laws. These predictable losses would not exist if space were filled with interfering matter. Even gravity itself reflects the dominance of emptiness. Gravitational fields extend through space uninterrupted, shaping motion without resistance. Planetary orbits remain stable for millions of years because there is almost nothing to slow them down. This is confirmed by precise tracking of satellites and planets, whose paths match calculations that assume near-perfect vacuum conditions. Laboratory experiments on Earth mirror this reality at smaller scales. Ultra-high vacuum chambers are designed to remove as much matter as possible because interference decreases as emptiness increases. Particle lifetimes, reaction rates, and force measurements become cleaner and more reliable in these conditions. The closer scientists get to emptiness, the more fundamental behaviors reveal themselves. What remains consistent across all these observations is that emptiness is not passive. It shapes outcomes by limiting interaction, preserving motion, and allowing systems to persist without disruption. Matter behaves the way it does because it is surrounded by vast regions where nothing interferes. This perspective removes the illusion that existence is crowded or continuous. Instead, reality is structured by separation. Objects influence one another across distance, fields extend through voids, and events unfold slowly because space allows them to do so. All available measurements continue to align with this picture. From atomic experiments to astronomical surveys, the data repeatedly confirm that absence dominates presence. And within that absence, the behavior of everything we observe becomes not only possible, but predictable, measurable, and stable over immense spans of time. As we reach the end of this exploration, what becomes clear is that emptiness is not a gap in our understanding, nor a missing piece waiting to be filled. It is a measured, persistent feature observed again and again through independent methods, across vastly different scales. From controlled laboratory experiments to deep space observations, the conclusion remains stable. Most of reality operates in conditions where interaction is rare, distance is dominant, and space itself sets the rules. This perspective changes how familiar concepts are understood. Solidity becomes an effect of forces acting across empty regions. Stability becomes a consequence of separation. Longevity becomes possible because encounters are infrequent. Nothing about this depends on interpretation or belief. It rests entirely on repeatable measurements, predictable equations, and observations that remain consistent regardless of where or how they are tested. What often goes unnoticed is how reliable this emptiness is. It behaves the same way everywhere it is measured. It does not fluctuate unpredictably, nor does it introduce randomness into physical laws. Instead, it provides a quiet framework in which those laws can operate without constant disruption. The more precisely it is measured, the more clearly its role emerges. In this sense, emptiness is not a background detail, but a defining condition. It allows motion without friction, signals without distortion, and systems without collapse. It explains why structures endure, why energy spreads the way it does, and why the universe remains intelligible to measurement and reason. When scientists continue to refine their instruments, pushing sensitivity further and deeper, they do not uncover a crowded reality hiding behind appearances. They consistently find the same thing: vast regions where almost nothing intervenes, and where that absence is exactly what makes clarity possible. Understanding this does not require imagination or metaphor. It requires only careful observation and acceptance of what the data show. Reality, at its most fundamental level, is shaped not by abundance, but by space. And within that space, everything that exists is given the conditions it needs to behave, persist, and be observed. If you found this exploration useful and would like more calm, precise examinations of overlooked scientific facts, you may consider subscribing and liking the video. Your support helps keep this kind of careful, evidence-based content available.